students, I am Dilip, Assistant Professor at LJ Institute of Engineering and Technology. Today in sequence and series, I will teach you new topic, that is radius of convergence of our series. So let's start. So today we will see what is radius of convergence, and in short form it is ROC, and interval of convergence. So let sigma n is from 0 to infinite an x minus a the whole raised to n be any power series. Here un equals to an into x minus a the whole raised to n. Therefore un plus 1, that is equals to, replacing n by n plus 1, so we have an plus 1 multiplied by x minus a the whole raised to n plus 1. Applying ratio test, limit n tends to infinite, modulus of un plus 1 upon un, this is equals to limit n tends to infinite, this is un plus 1 upon, this is un. Now we will simplify this result. So this is equals to limit n tends to infinite, an plus 1 upon an will be as it is. This is x minus a the whole raised to n plus 1, and this is x minus a the whole raised to n. So x minus a the whole raised to n will cancel out, and we have x minus a the whole raised to 1. Now x minus a is not a function of n. So writing this one as modulus of x minus a multiplied by limit n tends to infinite, modulus of an plus 1 upon an. Now this is modulus of x minus a. Now say this is equals to n. Using conditions of ratio test, for modulus of x minus a into L less than 1, that is for modulus of x minus a less than 1 upon L, power series converges. And for modulus of x minus a into L greater than 1, that is for modulus of x minus a greater than 1 upon L, power series diverges. For modulus of x minus a equals to 1 upon L, the test fails, hence we have to apply another test. Now you have to note down this important point, that is r equals to 1 upon L is called radius of convergence. For given power series, sigma n is from 0 to infinite an x minus a the whole raised to n, there are three possibilities. First one is the series converges for all x when r equals to infinite. Second one is the series converges for x equals to a when r equals to 0. And the third one is if capital R is any non-zero positive real number, then the series converges for modulus of x minus a less than r and diverges for modulus of x minus a greater than r. The interval in which the series converges is called interval of convergence. Now we have one example related to this topic, that is find the radius of convergence and interval of convergence of the series sigma n is from 0 to infinite minus 3 raised to n into x raised to n upon square root of n plus 1. So here is the solution. Here un equals to minus 3 raised to n into x raised to n upon square root of n plus 1. So first of all we will find out un plus 1. So for that purpose in un we will replace n by n plus 1. So un plus 1, that is equals to minus 3 raised to n plus 1 into x raised to n plus 1 upon square root of, if you will replace n by n plus 1, so it will become n plus 1 plus 1. So it is square root of n plus 2. Here we are going to apply ratio test. Therefore, limit n tends to infinite, modulus of un plus 1 upon un. This is equals to limit n tends to infinite. This is un plus 1, and multiplying this result by the inverse of un, that is this one, and that is square root of n plus 1 divided by minus 3 raised to n into x raised to n. Now we have to simplify this result. So this is equals to limit n tends to infinite. This root n plus 1 upon root n plus 2 will be as it is. Now x raised to n will cancel out. So we will be having x raised to 1 only, and minus 3 raised to n will cancel out. We will be having minus 3 raised to 1, it means minus 3 only. Now modulus of minus 3x, it will become 3 into modulus of x, and which is not a function of n. So writing this one as 3 into mod x into limit n tends to infinite square root of n plus 1 upon n plus 2. Now 3 into mod x, limit n tends to infinite, taking n common from the numerator and denominator, and it will cancel out, and we have 1 plus 1 over n upon 1 plus 2 over n. Now as n tends to infinite, 1 upon n and 2 upon n tends to 0. So this result is going to be 1, and if we multiply 1 by 3 into mod x, the result is 3 into mod x. Now we will apply the conditions of ratio test. By ratio test, the series converges for 3 into mod x less than 1 and diverges for 3 into mod x greater than 1. Means it converges for mod x less than 1 by 3. So we have mod x less than 1 upon 3. And mod x less than 1 upon 3, that is nothing but minus 1 upon 3 less than x less than 1 upon 3. And diverges for mod x greater than 1 upon 3. Here the radius of convergence r is 1 upon 3. Now if mod x equals to 1 upon 3, that is x equals to plus minus 1 upon 3. When mod x equals to a, then we have x equals to plus minus a. So here if mod x equals to 1 upon 3, then x equals to plus minus 1 upon 3. Now we will check the convergence of the given power series for x equals to 1 upon 3 and x equals to minus 1 upon 3. If x equals to minus 1 upon 3, then un equals to minus 3 raised to n, replacing x by minus 1 upon 3. So it is minus 1 upon 3 the whole raised to n upon square root of n plus 1. Now minus 3 raised to n and minus 3 raised to n will cancel out. So we have in the numerator, which is 1, upon in the denominator we have root n plus 1, and this is equals to 1 upon, taking n common from the denominator, so we have root n into square root of 1 plus 1 upon n. So now take Vn equals to 1 upon root n. Here we are going to apply comparison test. Limit n tends to infinite un upon Vn. This is equals to limit n tends to infinite. Now this is un. Now if you will divide it by Vn, which is 1 upon root n, so root n will cancel out. So we have limit n tends to infinite 1 upon square root of 1 plus 1 upon n. Now as n tends to infinite, 1 upon n tends to 0. So we have 1 upon square root of 1 plus 0, that is 1, which is finite and non-zero value. Now sigma Vn, that is equals to sigma 1 upon square root of n, is a p series with p equals to 1 by 2, which is less than 1. So series sigma Vn is divergent. Therefore by limit comparison test, sigma un is also divergent for x equals to minus 1 upon 3. Now if x equals to 1 upon 3, then un equals to minus 3 raised to n, replacing x by 1 upon 3, so it is 1 upon 3 the whole raised to n, divided by square root of n plus 1. So 3 raised to n will cancel out, and this is equals to minus 1 raised to n upon square root of n plus 1. Now this is an alternating series, so to check the convergence of this series we will apply Leibniz test. Therefore, first condition, modulus of un minus modulus of un plus 1. This is modulus of un, neglecting minus 1 raised to n. So this is 1 upon square root of n plus 1 minus, now this is modulus of un, and if you will replace n by n plus 1 in modulus of un, you will get modulus of un plus 1. So it is minus 1 upon square root of n plus 2, and this is greater than 0. So we have modulus of un minus modulus of un plus 1 is greater than 0. Therefore, we have modulus of un is greater than modulus of un plus 1, and limit n tends to infinite, 1 upon square root of n plus 1. As n tends to infinite, 1 upon square root of n plus 1 tends to 0. So the limit of 1 upon square root of n plus 1 is 0. Therefore, by Leibniz test, the series sigma un is convergent for x equals to 1 upon 3. Thus the series sigma n is from 0 to infinite minus 3 raised to n x raised to n upon square root of n plus 1 converges for minus 1 by 3 less than x less than or equals to 1 upon 3. Hence the interval of conversion is open interval minus 1 by 3 to close interval plus 1 by 3. Now this is the second example. Find the interval of convergence of the series sigma n is from 0 to infinite x raised to n upon n factorial. So here is the solution. Here un equals to x raised to n upon n factorial. So first of all we will find out un plus 1. So for that purpose we will replace n by n plus 1 in un. So un plus 1, that is equals to x raised to n plus 1 upon n plus 1 factorial. Now we will apply ratio test. Therefore limit n tends to infinite, modulus of un plus 1 upon un, this is equals to limit n tends to infinite, this is un plus 1, that is x raised to n plus 1 upon n plus 1 factorial, multiplying it by inverse of un, that is n factorial upon x raised to n. So x raised to n will cancel out, and we will be having x raised to 1 in the numerator, and writing n plus 1 factorial as n plus 1 into n factorial. So n factorial will cancel out. So this is equals to limit n tends to infinite, n factorial upon n plus 1 into n factorial into x raised to 1. So n factorial will cancel out, and this is equals to mod x into limit n tends to infinite 1 upon n plus 1. Now as n tends to infinite, 1 upon n plus 1 tends to 0. So this is equals to mod x into 0, and that is equals to 0, and 0 is less than 1. Therefore the given series is convergent for all x by ratio test. Hence the interval of conversion is open interval minus infinite to plus infinite. So in today's lecture we have discussed what is radius of convergence and interval of convergence, and we have gone through examples related to this topic. Thank you for watching this video. I will see you in the next lecture.